Section: Introduction. In this section, we discuss the increasing presence of generative AI in our daily lives, such as through ChatGPT and GPT-4, as well as the demand for AI-generated content in various industries, particularly in multimedia. To meet the need for quick creation of audiovisual content, effective text-to-audio models are essential. One approach to enhance these models is through supervised fine-tuning based direct preference optimization, DPO, which is a cost-effective alternative to reinforcement learning with human feedback, RLHF, for aligning AI responses with human preferences. We focus on applying the DPO diffusion approach to improve the alignment between input text prompts and audio outputs in a text-to-audio model called Tango. We fine-tune Tango using a synthesized preference dataset, named Audio Alpaca, which consists of diverse audio descriptions paired with preferred and undesirable audios. The preferred audios accurately reflect the text descriptions, while the undesirable audios contain flaws like missing concepts or high noise levels. To generate the undesirable audios, we perturb the descriptions and use adversarial filtering to select audios with low clap scores. We carefully select samples for DPO fine-tuning based on clap score differentials to ensure proximity to the prompt while maintaining a distance between preference pairs. Our experiments show that fine-tuning Tango on the pruned Audio Alpaca dataset results in Tango 2, which outperforms Tango and AUDIO-LDM2 in both objective and human evaluations. The key contributions of our work include developing a cost-effective method for creating a preference dataset for text-to-audio generation, sharing the Audio Alpaca dataset, demonstrating the superior performance of Tango 2 without additional data, and showcasing the effectiveness of Diffusion-DPO in audio generation. In the related work, models like Audio LDM, Make an Audio, Tango, and AudioGen have gained attention for text-to-audio generation. These models utilize diffusion architectures for audio generation from text prompts. Recent advancements include Audio LM, which uses W2V-BERT for generating semantic tokens from audio prompts, and Baton, a framework for aligning generated audio with human perception through a reward model. Our approach differs by automatically constructing a pairwise preference dataset, Audio Alpaca, and training Tango on this dataset using Diffusion-DPO to generate human-preferred audio samples. Section Summary. In this section, we introduce the growing role of generative AI in our daily lives, such as through models like ChatGPT, GPT-4, Stable Diffusion, and DALL-E3 for creating AI-generated content. We focus on enhancing text-to-audio models by utilizing a supervised fine-tuning based direct preference optimization (DPO) approach to align audio outputs with human preferences, resulting in the development of Tango 2 that outperforms previous models like Tango and AUDIO-LDM2 in both objective and subjective evaluations. Our work contributes by providing a cost-effective method for creating a preference dataset for text-to-audio generation, sharing the Audio Alpaca dataset, and demonstrating the effectiveness of Diffusion-DPO in audio generation. Section: Background. In this section, we will provide an overview of Tango. Tango, proposed by a group of researchers, mainly relies on a latent diffusion model, LDM, and an instruction-tuned LLM for generating audio from text. It consists of three main components: a textual prompt encoder, a latent diffusion model, LDM, and an audio VAE with a vocoder. The textual prompt encoder encodes the input description of the audio. This encoded text is then used to create a latent representation of the audio from standard Gaussian noise using reverse diffusion. The MEL spectrogram VAE decoder then generates a MEL spectrogram from this latent audio representation, which is fed into a vocoder to produce the final audio output. For the textual prompt encoder, Tango utilizes a pre-trained LLM called Flan T5-LARGE to acquire text encoding, where specific parameters represent the token count and token embedding size. The latent diffusion model in Tango aims to construct the audio prior guided by the text encoding. This involves approximating the true prior using parameterized processes through forward and reverse diffusion. The forward diffusion involves sampling versions of the audio prior with scheduled noise parameters, while the reverse process reconstructs the audio prior using text-guided noise estimation. The audio VAE compresses the MEL spectrogram of an audio sample into an audio prior, which is then reconstructed using input text guidance by the latent diffusion model. Both the encoder and decoder of the audio VAE consist of Res-U-Net blocks and are trained using specific optimization techniques. Tango utilizes the hi-fi GAN vocoder to convert the MEL spectrogram generated by the audio VAE decoder into audio. Additionally, Tango incorporates a data augmentation method that merges two audio signals while considering human auditory perception. This involves adjusting the weights of the signals based on their pressure levels to prevent one signal from dominating the other. In summary, Tango leverages advanced models and techniques to generate high-quality audio from text inputs, providing a comprehensive framework for text-to-audio generation. Section Summary. In this section, we introduce Tango, a text-to-audio generation model that relies on a latent diffusion model, LDM, and a text encoder. The LDM in Tango constructs audio prior guided by text encoding through forward and reverse diffusion processes, while the text encoder utilizes a pre-trained language model for text encoding. Additionally, Tango employs an audio VAE and vocoder, utilizing Res-U-Net blocks and hi-fi GAN for audio reconstruction and generation, along with a data augmentation method that considers human auditory perception by adjusting the weights of merged audio signals based on their pressure levels. Section: Preference Optimization for Language Models. In this section, we will explain how we optimize preferences for language models. Tuning large language models, LLMs, to generate responses that align with human preference is a key focus for the ML community. The popular method for this alignment is reinforcement learning with human feedback, RLHF, which involves several steps. First, we perform supervised fine-tuning, SFT, where the pre-trained LLM is fine-tuned on high-quality tasks to get the fine-tuned model. Next, we use reward modeling where the fine-tuned model is given an input to generate responses that are then ranked by human labelers. The preferences are modeled using methods like Bradley-Terry, BT, which helps in learning the human preference distribution. We then move on to RL optimization where we use the learned preferences to improve the language model. This optimization process involves a learning objective that includes the reference model, supervised fine-tuned model, the policy language model, to be enhanced based on feedback, and a control to prevent significant divergence from the reference model. Our methodology consists of creating a preference dataset called Audio Alpaca and using DPO for alignment. We start by generating audio samples from text prompts using the Tango model. We follow two strategies. One involves generating multiple inferences from the same prompt, and the other involves inferences from perturbed prompts. In the first strategy, we select diverse captions, cluster them, and generate audio samples with different denoising steps. In the second strategy, we perturb the captions using the GPT-4 model to create variations and generate corresponding audio samples. These strategies help us create a diverse preference dataset for further alignment of language models. Section Summary. In this section, we delve into the process of optimizing preferences for language models, particularly large language models, LLMs, to align their responses with human preferences. The key steps involve supervised fine-tuning on downstream tasks, modeling human preferences using techniques like Bradley-Terry, BT, and leveraging reinforcement learning methods like PPO to provide feedback to the language model based on the learned preferences. Additionally, our methodology includes creating a preference dataset called Audio Alpaca and utilizing the DPO approach for alignment, which involves generating audio samples from text prompts using the Tango model and exploring strategies like multiple inferences from the same prompt and inferences from perturbed prompts. Section: Strategy 3. Inferences from temporally perturbed prompts. In this section, we focus on Strategy 3, which involves making inferences from prompts that involve the sequence and timing of events. To identify such prompts in the AudioCaps training dataset, we search for keywords like before, after, then, or followed. These prompts are labeled as set 69 number 69. For each caption in set 69 number 69, we ask GPT-4 to create variations by changing the event order or adding, removing events. These variations are called temporally perturbed captions. We guide GPT-4 in generating these variations with specific instructions, as shown in tab data_generation_example. The perturbed captions are paired with audio samples following the same process as in Strategy 2. Similar to Strategy 2, the perturbed captions are only used to create the audio samples and not for preference data creation elsewhere. The paired text prompts and audio samples from all three strategies are combined into a dataset labeled as 73 number 73, with 74 number 74 denoting the set of 4 or 2 generated audio samples depending on the strategy. For Strategy 1, we compute the clap matching score between a text prompt and all audio samples. The audio sample with the highest matching score is considered most aligned with the text prompt and labeled as the winning sample, while the others are labeled as losing samples. This process generates preference data points for the losing audio samples. For Strategy 2 and 3, we compare the clap scores between the text prompt and the audio samples. The audio sample with a higher score is chosen as the winning audio, while the other is the losing audio. Preference data points are created based on these comparisons. To ensure strong alignment between the winning audio and the text prompt, we use clap scores as a measure. The winning audio must have a minimum clap score with the text prompt, while the losing audio must also meet a minimum clap score requirement. Additionally, the winning audio must have a higher clap score than the losing audio concerning the text prompt. We set thresholds for the difference in clap scores to ensure the losing audio is sufficiently different from the winning audio. An ensemble filtering strategy using 2 clap models is employed to enhance the selection process. After applying these conditions, our preference dataset, Audio Alpaca, contains 15K samples. The distribution of Audio Alpaca is detailed in tab Strategies. Section Summary. In this section, we focus on deriving inferences from temporally perturbed prompts in the AudioCaps dataset. By identifying specific keywords like before or after in prompts, we create temporal perturbations using GPT-4 to generate audio samples. We then use clap matching scores to select winning and losing audio samples based on alignment with the text prompts, ensuring a strong alignment for the winning audio and semantic closeness for the losing audio in our preference dataset Audio Alpaca. Section DPO for preference modeling. In this section, we will discuss preference modeling. Unlike RLHF, DPO has become a more robust and practical alternative for LLM alignment. DPO allows the model to learn from both desirable and undesirable outputs, unlike supervised fine-tuning, SFT, which only focuses on desirable outputs. The DPO objective is derived by replacing the optimal reward from RLHF in the negative log likelihood loss. This approach has been extended to diffusion networks to maximize a specific learning objective with a defined reward along the entire diffusion path. By applying Jensen's inequality and leveraging the convexity of the process, we can simplify the final form of the DPO objective for diffusion networks in terms of L2 noise estimation losses. We fine-tuned our model using the Tango full FT checkpoint on our preference dataset, Audio Alpaca, which contains 15,025 preference pairs. We used Atom W optimizer with a specific learning rate and scheduler for fine-tuning. The DPO loss parameter was set as recommended in previous work. Our training process involved 1 epoch of supervised fine-tuning followed by 4 epochs of DPO on prompt and preferred audio samples. The entire fine-tuning process took about 3.5 hours on 2 A100 GPS with specific batch sizes and gradient accumulation steps. We compared our model, Tango 2, with 3 strong baselines, AUDIOLDM, AUDIOLDM 2.2, and Baton. These baselines utilize different approaches such as joint audio text representation models and reward-based training. Baton, for instance, focuses on maximizing rewards through supervised fine-tuning based on human preferences. However, the dataset and code for Baton have not been publicly shared for comparison. Section Summary. In this section, we introduce DPO for preference modeling as a robust and practical alternative to RLHF for LLM alignment, allowing models to learn from both desirable and undesirable outputs. By substituting the optimal reward in the NLL loss, the DPO objective is derived, which has been extended to diffusion networks to maximize learning objectives along the diffusion path. Our experiments fine-tuned models on the audio alpaca dataset using DPO, achieving promising results compared to strong baselines like AUDIO-LDM and Baton in text-to-audio modeling. Section: Objective Metrics. In this section, we assess the quality of the text-to-audio generation using various metrics like Frechet audio distance, FAD, KL divergence, inception score, IS, and clap score. FAD measures the difference between generated and reference audio samples at a distribution level, while KL divergence compares the acoustic event probabilities of the real and generated audio samples. IS evaluates the specificity and coverage of a set of samples, and clap score measures the similarity between the audio and its textual description. We use the Audio LDM evaluation toolkit for these assessments. Our subjective evaluation focused on two main aspects: overall audio quality, OVL, and relevance to the text input, REL. OVL measures the general sound quality and naturalness, while REL assesses how well the audio matches the input text. Annotators rated each audio sample on a scale from 1 to 5 for both OVL and REL. We conducted this evaluation on a subset of 50 prompts from the AudioCaps test set, with each sample reviewed by at least 4 annotators. When comparing Tango 2 with Tango and AUDIO-LDM2, we found that Tango 2 showed improvements in objective metrics like FAD, KL, IS, and clap scores. Tango 2 performed better in audio quality and alignment with the input text compared to the other models. Our subjective evaluation also revealed that Tango 2 received higher ratings for both overall quality and relevance, indicating its superiority over Tango and AUDIO-LDM2. We further analyzed the performance of Tango and AUDIO-LDM2 on prompts with multiple sequential events and found that Tango 2 consistently outperformed the other models in both temporal and non-temporal scenarios. This improvement can be attributed to the training process that focuses on generating preferred audio outputs while penalizing undesirable ones. Overall, Tango 2 demonstrated superior performance in generating audio that aligns well with the input text across various metrics and scenarios. Section Summary. In this section, we evaluated the text-to-audio generation using objective metrics like FAD, KL divergence, IS, and clap score. Tango 2 showed significant improvements in objective metrics, outperforming baselines like Tango and AUDIO-LDM2, particularly excelling in KL and IS scores. Additionally, Tango 2 achieved high ratings in subjective evaluations for overall quality and relevance, surpassing both Tango and AUDIO-LDM2, showcasing the benefits of preference modeling on audio alpaca. Section: Ablations on audio alpaca. In this section, we conducted an ablation study on audio alpaca to explore how different ways of creating negative data affect its performance. When we excluded data samples generated by strategies 2 and 3, we observed a significant decrease in the performance of Tango 2, as shown in tab Main Results. This highlights the importance of making changes to event and temporal prompts. During our experiments, we discovered that using filtering to generate various versions of audio alpaca can influence its performance. See Sec. Pref dataset. The impact of this filtering process is illustrated in Fig. Filtering. We found that setting 153 number 153 and 154 number 154 produced the best results.